So my goal in this presentation is to convince you in the next half an hour that system theory can be done without transfer function or state space representations. The classical approach, which follows the red line in the figure, is we, using some observed data, derive a model using model identification, and based on the model and some design specifications, derive the desired solution, which can be controller or a filter or control signal or filter signal. This presentation is about the direct path in blue, which goes from the given data without parametric modeling to the desired solution. And low-rank approximation methods play a key role in this problem. One approach is illustrated here on example. So if we have a data-driven forecasting problem, we are given past data of a time series in blue, and we want to predict the future values in red. And if we put the data in a Hankel matrix, and we have the prior assumption that the data is a sum of damped exponential signal, then we know that the rank of the Hankel matrix is bounded. So this property of bounded rank allows us to solve the matrix completion problem, which generates the future samples directly from solution of the matrix completion problem. So it's a powerful idea that we can pose and solve in this case, prediction problems as matrix completion problems or missing data estimation problems. However, you know that you're experts in low-rank matrix completion and approximation. These are hard to solve in general non-convex optimization problems. And the Hankel structure in this case is an extra constraint that puts even more difficulty apparently in the problem. So what I'm considering in this presentation is a slightly different problem. In some sense more general, in other cases, in other senses more restrictive, because I'll assume that apart from the trajectory that I want to fill the missing data in, like here the red samples, I have another trajectory of the system, which I call the data trajectory. And in this case, let me show one simulation of what I'm going to do in the presentation. That will be a running example throughout the presentation. I have in the background a true data generating system, which is in this case sixth order autonomous linear time invariant system. And I have two trajectories. One is with 100 samples. This is the data trajectory. And the other trajectory is specified with only n, where n is the order of the system, in this case 6 samples, which I moreover take random. These are the red points in the figure. And by doing the 3 lines, which are construct a Hankel matrix with this function block Hankel and solve a system of linear equations and do matrix multiplication, I find interpolation of the data points, the given data points, which I can show you in the presentation. I can guarantee is also a trajectory of the same system that generated the data. So this is in a nutshell the idea that we can do this missing data estimation or interpolation of trajectories directly from data with a very simple method, which is solving system of linear equations. So what stays behind this methodology is a data-driven representation, which is general for linear time invariant systems. I used the example for autonomous, but it can be input-output system. And this will be the alternative to using the parametric models like transfer function or state space. So that's what I advertise you. And to prove that this is a viable alternative to state space and transfer function models, I'll solve apparently a new problem. I don't find anywhere in the literature the solution to this general interpolation of trajectories problem. In the first 2 parts, I'll assume exact data. And this assumption will be relaxed in the 3rd part of the presentation, where I will consider various generalizations and validate the results empirically on real data. So we start with the methodology. I'll stop in every transition from one section to another to ask for questions. So if you have any doubts or questions or comments, you can post them in the chat and I'll answer them as soon as I have chance. So the methodology is strongly based on what is known as the behavioral approach in system theory, which views the dynamical system as a set. This is very different from the classical input-output point of view. It's in many ways more general, and it allows us in particular to use this very concise set theoretic notation, W belongs to B, which we can in words interpret as the signal W is a trajectory of the system B. Or if you view it from a system identification perspective, the same statement means that the model B is exact for the data W. Although this is very general, I'll use it for the special case of linear time invariant systems. So in this case, B is a set which has the property of being shift invariant subspace. So that's what means that the model is LTI, linear time invariant. But apart from the shift invariant subspace structure, the LTI system has additional finer structure which is described by what are called integer invariants. So I don't want to go in the full details of the system theory behind this. What will matter for this presentation is that there are three important characteristics of the set B, which are the number of inputs that has nothing to do with already fixing the input-output partition into the classical point of view of map from input to output, but it's a invariant of the set, which is happens to be the same as the number of inputs. Another one is order, which also is related to the minimal state dimension in a state space representation, and the luck, which is related to, which is the observability index in a state space representation. So the first question that we'll consider is important in system identification. This is the identifiability question. Given a trajectory WD of a linear time invariant system, under what conditions on the data the system can be recovered back from the data? Since we know that the system is linear time invariant, we can do a construction which is shown here. So we take the span of the given trajectory as well as all its shifts. Assuming that the trajectory is infinite, this means that we have a whole set of infinite set of trajectories of the system, and we take linear combination of these trajectories. So this is what I'll call B hat, the identified system. And by construction, this system is linear time invariant. And also it is because of the properties of shift invariance and linearity of the original system, it is included into the original system. Now, when this inclusion holds true with equality, then we have identifiability, because then we can conclude that the identified system, which is constructed only from the data and the prior knowledge of linearity and time invariance, is recovering the true system. So that's an important result. However, this result is for infinite trajectories. What I'm going to do next is to generalize it to finite, or rather modify it for finite trajectories. So we consider first some notation, restriction of a trajectory, infinite trajectory, or a system on a finite interval 1 to capital L is denoted with bar sub L notation. So this means that we cut only the first part of the trajectory. Because of time invariance, the interval is not important, only the length of the interval, the capital L, matters. And here is one very important formula. The dimension of the restricted set of trajectories B bar L, which is called the behavior, the restricted behavior, is a subspace of dimension. This integer invariants now come into play, number of inputs times L, which is the length of the horizon, plus order. The formula should make sense from a system, from state space point of view, because the first term, M times L, is actually the degrees of freedom in choosing the input. And the second term is the degrees of freedom due to the initial conditions. Second fact, which I'll use later, is that two systems, B and B prime, are equal if and only if their restrictions on a finite interval are equal, provided that this interval has sufficient length, and sufficient means that it is at least maximum of the lags of the two systems plus one. So now we do the construction of the identified system for finite trajectory, which has capital T samples. And we have a hyperparameter capital L, which is integer smaller or equal to capital T. So what we do is we do again shifting of the trajectory a finite number of times because it's finite, and at the same time cutting to the length L. So you can think of this as we take a window of length L and we slide it over the long trajectory with capital T samples. Every time we slide the window, we get a new trajectory, and this gives us in total capital T minus L plus 1 L samples long trajectories that we can put next to each other in a matrix. And this matrix is what is called the Hankel matrix of the data with depth L. Now, the image of the Hankel matrix is the equivalent of the identified model for the case of finite horizon. And this identified model, again, as in the infinite horizon case, is included into the restricted behavior of the true system with horizon L. So now we are ready to state the identifiability condition. First step is that we can conclude the quality of the identified and the true system based on the restriction, as I showed before, to a finite horizon. The second step takes into account the fact that the identified system is included into the true system so that these two systems are equal as subspaces if their dimensions are equal. And finally, using the fact that the dimension of the identified system is equal to the rank of the Hankel matrix, and the dimension of the true system can be expressed in terms of the integer invariance, we have explicit condition for identifiability, which is verifiable from the data and the prior knowledge of the number of inputs, order, and lack of the system. So this is the identifiability condition. In this case, we had to restrict, we didn't have to restrict to horizon larger than lag plus 1, but if we take a general horizon capital L, again, we can have the equality between the identified system and the image of the Hankel matrix with depth L, if and only if a rank condition holds. Now we have not lag plus 1, but capital L times m plus n equal to the rank of the Hankel matrix. So this is a simple condition to check, again, based on rank check and prior knowledge of integer invariance. This is an alternative to other conditions which are known in the literature as fundamental lemma, which are only sufficient, and they're derived more from the perspective of input design. So in the fundamental lemma, the given trajectory WD is split into inputs and outputs. The rank condition, similar to the one that I showed, is only in terms of the inputs. So this is the third condition. And this third condition has the name persistency of excitation. And in addition, which is a very important condition, the system is assumed to be controllable. So under these three conditions, we can conclude also identifiability. However, these three conditions are more difficult to verify from the data due to the controllability assumption, and also controllability excludes, for example, my running example, which is autonomous system and therefore not controllable. So we'll be using the more general rank condition that I presented in terms of the full trajectory, and I can call it generalized persistency of excitation. So this concludes the methodology part. I can stop for questions if there are any questions at this point.
There was a question, but I think that it was self-answered.
Okay, that's good. So if there are no other questions, then I continue with the second part, which is now exploiting this methodology for solving a problem, and this is the interpolation problem that I started with in the introduction. Now I'll define it more general. So we have two trajectories. The first one, which I call the data trajectory, is with length capital T. It's generated from an unknown data generating system B. And the second trajectory is actually partially specified with a very flexible way to take samples of this trajectory. So the given samples can be arbitrarily sampled among variables as well as in time. And now I use new notation that this bar index I given is not anymore an interval or samples in time, but they can be elements of the time series viewed as a matrix. So now the problem is we want to find a trajectory W hat, which is also a trajectory of the unknown system B, and it interpolates the given data at the moments of points where we have the given samples. So this problem in its full generality may have no solution or may have infinite number of solutions. And the first thing is to analyze when it has unique solution, because that will be the most interesting case for missing data estimation. So I state two conditions. The first one is just the condition I gave for the data-driven representation, the rank condition on the Hankel matrix having maximum rank, sufficiently high rank. This condition depends on the prior knowledge of the integer invariance of the system, as I said before. The second condition is that the given partially specified trajectory has exact completion. Now, it's not difficult to see, but I'm not going to elaborate on this, that this condition can be checked via the rank conditions here. So if these two conditions are satisfied, then it can be shown that the interpolation problem has exact solution. However, this solution may not be unique. So for uniqueness, we need a third assumption, which is has to do with the intuitive idea that we have enough samples to fix uniqueness. And what means enough? It turns out it's more complicated than just number of samples. We need also these samples to be at the right place. And again, this exact statement when the samples are sufficient for uniqueness is a rank test. So with these three conditions, we have unique solution. And if we have this unique solution, now we can ask the question how we compute it. And here is the surprisingly, embarrassingly simple solution, comes from the data-driven representation. So we know that W, the complete trajectory, is in the image of the Hankel matrix of the data trajectory WD. So this means that there exists a vector G, which multiplying Hankel matrix of WD gives you W, which is partially specified. Select from this system of linear equations the rows, the equations that are corresponding to the given samples in W. This gives us a system of equations here in step one. Solving this system for G, even though the solution may not be unique, will give us interpolant, so that by construction, the W hat, which is defined as the full Hankel matrix multiplied with G, will interpolate the data. And also due to the fact that this is the data-driven representation of the true data generating system, this W hat satisfies the condition that it is a trajectory of the system. And when the uniqueness assumptions are satisfied, we'll be sure that we recover the missing values exactly. So back to the simulation example, now I put all the given samples in the beginning. The first n, 6 samples are the given points. I take them again random, and I do the exact same calculation as before, namely solve, as I showed in the previous slide, solve the system of equations, multiply the Hankel matrix with the solution, and this gives me the interpolant. What I do next is I simulate with the function initial of MATLAB the actual data generating system D from the initial conditions, which are the first n samples. And what I verify is that the norm of the difference between the simulated trajectory from the model and the data-driven interpolant are equal up to numerical errors. What I can do, and it's equally easy with this algorithm, is to shift the data points in the end, which would be simulation with terminal conditions, or as I showed in the beginning, they can be randomly spread over the trajectory. So this is general, although I do it here in a special case of autonomous scalar system. It can be applied for general MIMO system and estimate the missing data. I was very quick with the second section, so there will be more time for questions.
I have one question. So are you assuming that the given samples are consecutive?
No, this is just an example in order to match the interpolation problem with the simulation problem.
So when you construct this Hankel matrix, if they are not consecutive, like will the matrix have like unknown entries or?
Let me remind you that there are two trajectories. So if we go back to the definition, so the WD trajectory is consecutive. This is complete trajectory. Now, the samples which are spread arbitrarily in time and variables are sampled from another trajectory, W, without the index D. So then, if I go to here, the Hankel matrix is constructed from the WD trajectory, which is complete. And I select the right-hand side of the system of equations from the given samples which can be spread arbitrarily.
I see, thank you.
Are there other questions at this point? Okay, I'll proceed then with a few generalizations. The first three are kind of trivial, but very useful. So what happens if the condition of of existence of exact interpolation is not satisfied? My assumption 2. Then we don't have exact solution of the system of equations, but we can solve the system of equations for G approximately in the least square sense. And that's what I do in this problem. So again, I have as a constraint of the optimization the fact that the interpolant is a trajectory of the system. This is due to the data-driven representation. W hat is the Hankel matrix times G for any G. And I look for the W hat which approximates as well as possible in the 2 norm the given samples. So this is approximation simultaneously as well as missing data estimation. On top of this, if I add equality constraints, I can also interpolate exactly some specified data points. So then I have full generality of fitting exactly some given samples, approximating other samples, and estimating yet other samples which are missing. It's only equality constraint least squares problem, convex optimization problem. It's easy to do numerically. Another generalization is that we can go from one given trajectory as data trajectory to multiple. So the only difference that happens in this case is that my data-driven representation now has matrix which is block matrix with Hankel blocks, every Hankel matrix corresponding to one of the data trajectories. And this is my running example. Now I take a complete trajectory, no missing data, and add noise to it. What changes in the algorithm is that instead of solving the system of equations with the backslash operator, I use the pseudo-inverse solving the least squares problem. And the red is the approximation of the true trajectory, which is in blue, and the data, which is the noisy one, is in dotted trajectory. So this is basically what is called in the literature errors in variables common smoother. Errors in variables because both the input and the output are noisy, but basically we do common smoothing. What immediately you can ask is how efficient is this method? Yes, it's not efficient because the computational cost grows quadratic with the length of the horizon L. Well, for classical methods which are parametric, like the Kalman filter, this will be linear complexity. So it's an open problem whether we can come up with efficient real-time computational method based on the data-driven representation without parametric model. Another generalization is, of course, what happens if we have noise also in the data trajectory. And here things become much more complicated, because if we define the maximum likelihood estimator with, let's say, classical assumptions of zero mean Gaussian noise, then we arrive, I don't show this, but this comes back to the Hankel structured low-rank approximation / completion problem in the beginning that I showed for the time series forecasting. We have completion due to the missing data, as well as approximation due to the noise. And this solution of this problem actually requires some sort of parametric representation of the model, maybe hidden, but still we need to parameterize the model. And also it leads to non-convex optimization problems, which is the major difficulty. Now, what is currently very active research topic is convex relaxations, either based on the nuclear norm, on the L1 normal relaxations, which from system theoretic point of view are using non-parametric modeling, and they lead to convex optimization. And third, and also very active at the moment, their topic is there are some partial results on solving problems of the sort I showed, simulation problems more specifically, and control problems for nonlinear systems. And the partial results at the moment are for finite impulse response Volterra, Wiener-Hammerstein, and bilinear systems. And it's interesting to see how far we can generalize these partial results to get some truly nonlinear data-driven simulation problems. So I give a few more details about the L1 normal regularization. It's based on the fact that the vector G that we use in the solution of the system of equations can actually be chosen to be sparse. And the sparsity is, again, this formula that you've seen multiple times, which gives the dimension of the restricted behavior. Now, imposing sparsity in case of noisy data, we can do with the L1 norm regularizer. So this leads to the classical lasso problem. And here the lambda parameter, the regularization parameter, is a trade-off between the fitting accuracy, which is the first term, and the sparsity, which is has to do, actually, you can relate with the order of the system in a parametric modeling. And in order to validate this relaxation, I take 6 data sets, which are, first one is taken from the Box-Jenkins classic time series analysis textbook. The other 5 are from the DAISY data sets that Miriam was using yesterday. And the table shows the number of samples, capital T, as well as number of inputs and outputs. All these data sets are split into input-output data. Although the method can work with general time series, all the data sets that I found are input-output data. And I use the first 3/4 of the data for my data trajectory WD, and the last 1/4 for validation, which is the to-be interpolated trajectory, and the setup is the simulation problem. So the missing data is the output of the validation data, given the input of the validation data. The evaluation of the performance is in terms of the relative estimation error, which is the relative output error expressed in percentage for the 3 methods that I compare. The 3 methods are the direct replacement, as I did in the errors and variables Kalman filter, of the backslash with the pseudo inverse, no hyperparameters in this case, the maximum likelihood method, which is the hard non-convex optimization problem, which I solve with local optimization, and the L1 norm regularization method. What you may quickly see is that the L1 norm regularization method with proper tuning of lambda, what I didn't had said, and it's important, is that for both maximum likelihood and the L1 norm regularization method, the hyperparameter is chosen by cheating, by knowing the exact output and finding the best value. So with this optimal choice of the lambda parameter in the L1 norm regularization, it gives the best results, and it outperforms the maximum likelihood method. This may look like a counterintuitive result, but it actually makes sense because we use non-parametric model, which is more flexible than the parametric one enforced by the maximum likelihood method. So it actually forces the solution towards something that may not be correct. And if I can just run over a few minutes to show how the lambda parameter is tuned, we basically grid the values of lambda and evaluate the evaluation criterion, which is the relative error. And you can see that the plots are not always neat, but kind of you can see the U-shape you expect, that there is some optimal value of lambda. In some of the cases, it's not quite U value. So this suggests that choosing the lambda parameter in practice, when you don't have the validation output, would be a challenging problem. Another thing I want to point out is on the right, I show the sparsity of the G solution. That's what we enforce with the regularizer. And this sparsity, in some examples, actually matches the theoretical sparsity that I showed based on the assumption that you have parametric model. So the red vertical line is the sparsity that you predict with fixed order of the system. And this is what the optimal tuning of lambda gives a sparsity. So in the first example, it actually matches. The second example gives sparser solution than the parametric model. And so on, you can see the different examples you get, sometimes match, sometimes not. So this leads me to conclusions. I hope I convince you that system theory can not only be done, but also is beneficial to do without transfer functions and state space representations. The key for this method is the data-driven representation, which is very constructive because it leads to general, simple, and practical computational method. It can be applied to the interpolation and approximation of trajectories problem, which is general and I would say generic problem in the sense that includes simulation, filtering, and output tracking control as special cases. It assumes only the LTI structure of the system without hyperparameters. And future work would focus on efficient methods, as I suggested, something of the sort of the Kalman filter, as well as statistical analysis of the results in case of noisy data and generalizations to nonlinear systems.
Thank you very much, Ivan. So now it's time for questions. Are there any questions?
I have one.
Go ahead.
Okay, thank you. Thanks for the very interesting talk. So I have two questions basically. So one is so let me phrase it in a better way. So when we do system identification or any Hankel kind of subspace identification methods, we get this matrices A, B, C, and of course, we can do this prediction and all, but they also will be useful for other downstream tasks when one is interested in designing a controller or analyzing stability and so on and so forth. With this approach, aren't we actually trading off those kind of downstream applications?
Correct. It all depends on the purpose. When I started, let me go back to my leading slide. My goal was to get from some given data, which can be both prior knowledge about the true system, as well as design specifications, as well as observed data, to desired solution. So what you're asking is all depending on what is the desired solution. If the desired solution is, like in this example, the prediction, then this direct method, which doesn't give you the model, is good enough. It gives you what you want. But if you want to get to some other things, not the prediction, but some properties of the model, then you can reformulate what is your desired solution and again ask the question, can I get directly to this information instead of going with a detour to computing more than what I want?
I see. Thank you. And the second question is about when we have the noise in the system, right, or the noise is added to the observed data, then the Hankel matrix is no longer will not have this low rank property, right?
Correct. Yeah.
So that's the one you're telling that that's the difficulty, or it's more than that?
Yeah, that's exactly right. So thank you for pointing this out, because it's a really important question. When we define the data-driven representation, we strongly depend on this rank deficiency property of the Hankel matrix. As long as we add even small noise to the Hankel matrix, the rank property is lost because it's non-generic. And then it's unclear how to recover back this subspace, which is the model. And this goes back to the whole question of the path from given data to model, how we enforce back this simultaneous rank deficiency and Hankel structure in the matrix. It is a difficult problem. How I managed to avoid it till the third part of the presentation, because I only added the noise on the to be interpolated trajectory and not on the data trajectory, which led to problems which are least squares problem with regressor matrix, which is exact. As long as your regressor matrix is noisy, as well as the right-hand side, then things become difficult. And therefore you need relaxations and all the stuff that I explained in the third part.
And again, there's this identifiability condition that has this persistency and rank condition, right? I mean, L times n plus n, correct? So based on my knowledge on systems theory, I mean, is this Navalina interpolation theory, or I don't remember. Basically, Hankel matrix has a finite rank, right? So that is as a known result for the finite dimensional linear systems. So what in specific this new result is trying here or capturing here?
Yes, so you're right. The rank is finite if you have exact data. The question is that this rank depends on the data. So the rank that I give here is the maximum rank you can get, and this gives you the identifiability. But if you choose unfortunate trajectory, which is not informative, so it doesn't reveal all the dynamics, then the rank of the Hankel matrix can be smaller than the one that is here in the formula, and then you don't have identifiability. So the test captures that you get to this maximum rank.